Hello everyone, I am Wenshuo.
I'm Mihaela.
I'm Serena, and we'll be talking about finding equilibrium in multi-agent games with payoff uncertainty. This is joint work with our advisors Ben Recht and Mike Jordan from UC Berkeley. So we'll start with some background on the basic two-player zero-sum game. In a game of rock, paper, scissors, we have player 1 and player 2, and a payoff matrix that represents the payoffs for player 1. This matrix says that if player 1 wins, player 1 gets 1 point and player 2 loses 1 point. In a two-player game, players can choose to always play a certain action, which is called a pure strategy, or they can choose each action with some probability, which is called a mixed strategy. Here, X is a vector containing the probabilities that player 1 plays each action, rock, paper, or scissors, or player 1's strategy. A pair of strategies is at Nash equilibrium if each player's strategy maximizes the expected payoff given each other player's strategy. In this case, the Nash equilibrium is for each player to play each action with equal probability. All of that previous setup assumed that both players knew the payoffs for all possible outcomes. In other words, the game had complete information. For games of complete information, Nash equilibria can be computed efficiently for zero-sum games, but even under complete information, this can be intractable to compute for general-sum games. But to make this even harder, in practice, the payoffs may only be partially known. For example, if player 1 and player 2 are two competing companies, they may be uncertain about the profit that comes from the actions that they take. Similarly, bidders in an auction may be uncertain about the true value of the item that they're bidding on. So in our work, we ask the question, how can we find equilibria in games that are robust to uncertainty in the game parameters? And in particular, we focus on payoff uncertainty. So going back to that first rock, paper, scissors example, suppose now we are uncertain about what the actual payoff matrix is. All we know is that the payoff matrix A comes from some uncertainty set U. As an example of an uncertainty set U, maybe the players know that if player 1 wins, the value that they gain is between 0 and 1. And if player 1 loses, the value that they gain is between -1 and 0. Our goal is to find a set of strategies that remains in Nash equilibrium for all feasible payoff matrices in the uncertainty set. If such strategies exist, they are known as ex post equilibrium. Formalizing the definition of an ex post equilibrium, suppose that the payoff matrix A again comes from some uncertainty set U. A pair of strategies is at an ex post equilibrium if they are at Nash equilibrium for all possible payoff matrices A in the uncertainty set U. Note that we don't assume any prior distribution of A over the uncertainty set U. All we know is that A belongs to this set. There is prior work on Bayesian equilibria, but we focus on the distribution-free worst-case setting. All we know is the uncertainty set U, which could, for example, be all convex combinations over a set of known payoff matrices.
In this work, we analyze equilibrium under payoff uncertainty for zero-sum one-shot games and for extensions to repeated stochastic games. In one-shot games, we show that if the uncertain game admits an ex post equilibrium, then it can be efficiently found via linear programming. In repeated stochastic games, the corresponding equilibrium concept is the ex post Markov perfect equilibrium. We show sufficient conditions for the existence of such equilibrium. Lastly, we show that the set of feasible values of two-player stochastic games can be found via dynamic programming. Let's first consider ex post equilibrium in one-shot games. Such an equilibrium point exists if and only if the point is in the set of Nash equilibrium for each feasible payoff matrix. For example, assume the only source of uncertainty is the rock-scissor outcome in the upper right corner. Smaller payoffs would make player 1 have a bias against playing rock. Thus, the equiprobable strategy is no longer equilibrium. A concrete example of a set that admits ex post equilibrium is where we are uncertain about the values of the wins and losses, but where we know that all win payoffs are equal among themselves, and similarly, all loss payoffs are equal among themselves. We can write this uncertainty as the convex combinations of these two extreme payoffs. Here, the equiprobable strategy 1/3, 1/3, 1/3 is a Nash equilibrium for both players. More generally, we show that if a zero-sum game has bounded polyhedral uncertainty and admits an ex post equilibrium, then it can be found via linear programming. Further, we provide a characterization for the maximal uncertainty set that corresponds to an ex-post equilibrium strategy. We can show that the payoff uncertainty in the previous example does not belong to the maximal uncertainty set of equiprobable strategy. On the other hand, if the payoff uncertainty admits ex-post equilibrium, then the solution to the following linear program is an ex-post equilibrium. Here, we present the simplified LP formulation in the case of two-player zero-sum games with payoff uncertainty, which can be expressed as the convex hull of a finite set of matrices.
Theorem 1 holds actually for more general n-player polymatrix games. Informally, an n-player polymatrix game can be expressed as a graph, where each node represents a player and each edge represents a two-player game between two nodes. The payoff for a given player is the sum of the player's payoffs from all his pairwise games. The game is zero-sum if the sum of the payoffs for all the players is 0. In such a game, the existing ex-post equilibrium can also be computed efficiently by linear programming. So far, we have been talking about one-shot games. What happens if the game can be played repeatedly? Now we consider stochastic games. Specifically, we consider an infinite time horizon where the game is played repeatedly for an infinite number of stages. And the transition dynamics among stages are captured by an MDP. The goal here for each player is to maximize his discounted expected payoff. An important focus has been on Markov perfect equilibrium, which refers to a perfect equilibrium of the dynamic game, where players' strategies depend only on the current stage. We assume that at each stage, the payoffs live in some bounded uncertainty set. We extend the idea of ex-post equilibrium to ex-post MPE, which refers to a perfect equilibrium of the uncertain game where players' strategies depend only on the current stage, under all feasible realizations of the uncertain payoffs. When the stage and action space are finite, such a game can exist on ex-post MPE, and we provide sufficient conditions for the existence. However, due to the uncertainty in the payoffs, the value of such a stochastic game cannot be fully determined. Instead, we show that any feasible value can be bounded up to a tight interval using dynamic programming. In sum, this work shows that existing ex-post equilibrium of one-shot games with payoff uncertainty can be computed efficiently and provides sufficient conditions for an ex-post MPE to exist in stochastic games with payoff uncertainty. There are several interesting future directions. First, we do not yet have necessary conditions for the existence of an ex-post equilibrium. Second, the results may be generalized to more general payoff structures and uncertainty sets. Also, uncertainty rewards can be a problem in practical reinforcement learning. We are interested in more potential connections of this work to other areas in reinforcement learning. For more details, please see our paper. Thank you.